Welcome to this video. This is video number 10 in my series of videos on Georg Cantor's contributions to the founding of the theory of transfinite numbers. In this video we're going to look at the final two sections of the work, which is section 19, which concentrates on the derivation of the normal form of the numbers from the second number class and the product form. There's also some material there on arithmetical properties that result directly, more or less, from the normal form of these numbers in the second number class. Now I'm going to go through the derivation of the normal form, not in fine detail, but I'm going to give a rough outline of how the normal form comes about. I'm also going to go through the product form, but the arithmetical properties I'm going to gloss over quite quickly. These are clear generalizations of the arithmetical properties that we came across in section 17, which was a couple of videos ago, and the derivations and the proofs of these arithmetical properties are fairly similar, even though we're dealing with slightly different expressions in some ways. The derivations run roughly along similar lines, so I'm going to skip some of the details when it comes to the arithmetical properties. And then we move on to section 20, which concentrates on the epsilon numbers of the numbers of the second number class. So here we have theorem A from section 19, which is, I'm not going to go through the proof of this, I'm just going to state the theorem, but I'm going to use this then to derive the normal form of numbers of the second number class. So every number alpha of the second number class can be brought in only one way, into the form alpha equals omega to the power of alpha naught, kappa naught, plus alpha primed, where 0 is less than or equal to alpha primed is less than omega to the power of alpha naught. 0 is less than kappa naught is less than omega, in other words kappa naught is finite. And alpha primed is always smaller than alpha, but alpha naught is smaller than or equal to alpha. I just want to concentrate for a second on the case when we've got alpha naught actually equal to alpha. Because here it says that alpha naught is smaller than or equal to alpha, but there's something particular that happens when we've got alpha naught is actually equal to alpha. So if alpha naught is equal to alpha, then we get that alpha from this up here, alpha is equal to omega to the power of alpha, kappa naught, plus alpha primed. We're also going to assume that alpha primed is not equal to 0. So alpha primed must be greater than 0. Well, in that case then, we get that alpha is going to be greater than omega to the power of alpha times kappa naught. Omega to the power of alpha times kappa naught is going to be in turn greater than or equal to omega to the power of alpha. So we're going to get equality only in the case when kappa naught is actually equal to 1. So that would suggest then that we get that omega to the power of alpha is less than alpha. But this is a contradiction to theorem F from section 18, which I stated right at the end of the last video. So if I just give a bit of a reminder of that, theorem F from section 18, we got that omega to the power of alpha is always going to be, or at least, we're not necessarily using the notation from theorem F section 18 here, but theorem F as applied to this particular situation here. So omega to the power of alpha is going to be greater than or equal to alpha. Well, that's a direct contradiction to this. So something's wrong with our initial assumptions. The thing that's wrong is this here, or one of the things that's wrong is this, that alpha primed is not equal to 0. So in other words, alpha primed must be equal to 0, and the whole thing here reduces to alpha equals omega to the power of alpha kappa naught. But now we've still got this to deal with, because we know that omega to the power of alpha times kappa naught is greater than or equal to omega to the power of alpha. So if kappa naught is greater than 1, then we're still in the same situation. Omega to the power of alpha is going to be less than alpha. So we must have then that kappa naught is actually equal to 1. In that case, we get that alpha is equal to omega to the power of alpha. So in the case where alpha naught is equal to alpha, this theorem will actually reduce to this here, alpha equals omega to the power of alpha. So for what we're going to be looking at over the next few minutes, we're going to be more interested in the case when alpha naught is strictly less than alpha. Although what we do does, strictly speaking, apply also to this case, it's going to be easier to visualize and to see what's going on if we consider when alpha naught is actually strictly less than alpha. In that case, there is a very real possibility this alpha primed is going to be non-zero. So let's have a look at this case now, where alpha naught is less than alpha. In this case, then there is the very real possibility that alpha primed is going to be non-zero. It could still happen, by the way, so I'm not ruling out this possibility that if alpha naught is less than alpha, we could still end up with something like alpha equals omega to the power of alpha naught. There's no guarantee that alpha is the smallest value for which we get alpha equals omega to the power of alpha. And that alpha primed will reduce to 0. So I'm not ruling that possibility out, it's not the possibility that we really want to consider here. We're going to assume then that alpha primed is non-zero, and we're also going to assume that it's not only non-zero but a number itself of the second number class. If it is a number of the second number class, then I can apply theorem A again to it and get something like alpha primed is equal to omega to the power of alpha 1, so alpha sub 1, kappa 1 plus alpha prime primed. And we're going to get some similar analogous inequalities relating to alpha 1 and alpha prime primed. In particular, we're going to get that 0 is less than or equal to alpha prime primed less than omega to the power of alpha 1. We're going to get that 0 is less than kappa 1 is less than omega, and we're also going to get that alpha, so here we had alpha primed is always smaller than alpha. Here we're going to get alpha primed is going to be less than alpha primed. And here we had alpha naught is smaller than or equal to alpha. Here we're going to get alpha 1. Again, okay, it could be equal to, but really we want to consider the case where alpha 1 is less than alpha naught. So we get some similar information relating to this particular expression. But now we're going to continue the process. Let's assume that alpha primed is not equal to 0. And is in fact itself a number from the second number class. Then I can apply theorem A again. I get alpha primed is equal to omega alpha 2 kappa 2 plus alpha primed. And I'm going to get a similar sequence of inequalities. So 0 less than or equal to alpha primed less than omega alpha 2. 0 is less than kappa 2 less than omega. Alpha primed is less than alpha primed, and alpha sub 2 is less than alpha sub 1. So I can continue this process, but I can't continue it in this process indefinitely. I can't continue it for an infinite number of steps, and here's why. Let's assume then well, we don't need to assume, we do have a decreasing sequence of these terms here. So we've got alpha is greater than alpha primed is greater than alpha primed is greater than alpha primed, and this is going to continue. So because all of these numbers, alpha primed, etc., form an aggregate of ordinal numbers, then because any aggregate of ordinal numbers is a well-ordered aggregate, there must be a least value. So let's say that somewhere along the line we get to alpha tau. So what are the possibilities here for tau, for alpha tau? This is a superscript, by the way, not a power. So alpha tau could be a number from the second number class. If so, then we just continue the process, just in the same way that we have been. But it will eventually happen that alpha tau is going to be a number of the first number class. Remember, we can't continue this process indefinitely because we have to arrive at a smallest value. Every aggregate of ordinal numbers has a smallest value. So if we just get an infinite sequence of inequalities, and each term is smaller than the previous term, then there will be no least value. But that can't happen. We have to get to a smallest value. So alpha tau can't be a number of the second number class, otherwise we continue the process. It must be of the first number class then. So in that case, we get alpha tau is going to be equal to, now this is not an application of theorem A, because theorem A only applies to numbers of the second number class, but what I'm about to write still applies. It's still true. It's going to be omega to the power of naught times kappa tau plus alpha with a tau plus 1 as the superscript, sorry, not subscript. And by section 18, theorem B, part A, omega to the power of naught is equal to 1. And if we choose kappa tau to be equal to alpha tau, then that will mean then that alpha tau plus 1 is going to be equal to 0. So what we may as well say then is that the smallest value that we arrive at is going to be 0. Okay, we always have to get to 0. This sequence won't decrease indefinitely. It will get to a point where we've got alpha tau plus 1 must be equal to 0. So what I'm going to see then is if I continue this process, it's going to kind of bottom out at some point. So I'm going to get alpha tau minus 1 is equal to omega alpha sub tau minus 1 kappa tau minus 1 plus alpha tau. And then the final stage is going to be alpha tau, which I can write as omega naught, omega to the power of naught, kappa tau, that's it. Okay, and then what I can start to do is to, working from the bottom up effectively, I can substitute this expression for alpha tau into here. Then I can substitute this expression for alpha tau minus 1 into the expression that would be above that. And I can continue this process. So this will end up going into here. And then this expression will end up going into here. Okay, so working from the bottom upwards, I can keep making these substitutions, and there's only a finite number of these. There's only a finite number of steps, and this is important. So this leads us to what's called the normal form of a number of the second number class, and this is theorem B, which I'm going to state in a second. So this is what we end up with, the normal form of any number from the second number class. So theorem B from section 19, every number alpha of the second number class can be brought in only one way into this form, where alpha naught to alpha tau are numbers of the first or second number class, such that alpha naught is greater than alpha 1, greater than greater than alpha tau, which is greater than or equal to 0, while kappa naught to kappa tau and the number tau plus 1, not kappa tau plus 1 but tau plus 1, are numbers of the first number class different from 0. I just want to comment on the fact that alpha tau here is greater than or equal to 0. In the example that I just gave, where I went through the repeated applications of theorem A, I might have inadvertently given the impression that we get to a point where alpha tau is going to be equal to 0. But that's not forced to be the case. It might be that earlier in the process, we get something like alpha tau is equal to omega alpha tau kappa tau, and where the plus alpha tau plus 1 here is actually equal to 0, in which case it would disappear. In this case, alpha tau will actually still be a number from the second number class. It's just that there's no plus anything here to apply theorem A to again. The argument that I was giving previously was that what happens if we get to a point where alpha tau is in the first number class, possibly not equal to 0. So it could actually happen that alpha tau is of the second number class, but that the alpha tau plus 1 just goes straight to 0. So it might well be that we've got a finite number of terms here, but the final power on the end here of omega might not actually be equal to 0. It might actually be greater than it. It might be in itself in the second number class. But the possibility of this being equal to 0 is there as well. You can compare this expression here, this normal form of every number of the second number class, to the kinds of expressions that we were working with in section 17, I think in video 8. The difference is that in video 8, section 17, we were dealing with a very restricted class of numbers from the second number class, namely when we've got something that looks like this, resembles this, but the powers of omega are all finite. So this is a clear generalization of what was going on in section 17, where we're actually allowing alpha naught, alpha 1 to be themselves transfinite numbers. This is only possible through what we've done in section 18, when we developed the idea of exponentiation as applied to transfinite numbers, particularly transfinite powers of numbers. Okay, so then from theorem B, we move on to theorem C, D, E, and F, which I'm not going to state, and I'm not going to go through in any detail, but these are really just arithmetical properties of numbers from the second number class that are almost immediate consequences of this normal form. And the forms of these theorems, the arithmetical properties, are very similar in many respects to what we saw in section 17. Again, they are clear generalizations which are applying to a larger class of numbers, but the forms really of the results are pretty much the same. I'm not going to go through all of these. The derivations are not particularly difficult. It's just that they're very repetitive and very tedious, really. So I'm not going to go through them. There are a couple of newer results that involve exponentiation, but again, these results are not particularly difficult to prove. Then we come on to theorem G, which I'm just going to state. I'm not going to go through the derivation. I'll just get rid of this here. So theorem G is the so-called product form of numbers of the second number class. So with using the arithmetical properties that have been proved in theorems C to F, we can go from here to here, to this result here. This is the product form of this number here. And just some things to point out here. The powers of omega, these gammas, now not alphas. In particular, we've got gamma naught is equal to alpha sub tau. Gamma 1 is equal to alpha tau minus 1 minus alpha tau. Gamma 2 is equal to alpha tau minus 2 minus alpha tau minus 1, up to gamma tau. And the kappas here are the exact same as what we've got up here. But notice that the order is kind of reversed. So here we had kappa naught, then we've got kappa 1, up to kappa tau right at the very end. Here we've got kappa naught right at this end. And we're working backwards this way and we get kappa tau right at this end here. And it has to be this way. Remember that multiplication of transfinite ordinals in particular is not commutative, so I can't shuffle these terms around without certain considerations. So the kappa naught has to go here in the same way that the kappa tau has to go here, and all of the others have to go in their respective places. So from theorem G, there's a couple more theorems just to finish off this section. Theorem H, which is looks at a particular case when we've got a number from the second number class of the second kind. It just gives a particular way that that can be written. I'm not going to go through that. And then the final two theorems, I and there is no theorem J, but theorem K, gives some conditions under which multiplication, addition and multiplication of numbers from the second number class is commutative. So this is what I've just been touching on actually, that commutativity in general doesn't hold for transfinite ordinals, but it does hold under certain conditions, and theorems I and K show under which conditions addition and multiplication of transfinite ordinals obeys the commutative laws. So now we move on to section 20, the final section of this work, in which we're going to look at the epsilon numbers of the second number class. So what are epsilon numbers? Well, let me explain. Going back to the normal form of alpha being a number from the second number class, then it has a unique representation, omega to the power of alpha naught, kappa naught, plus omega to the power of alpha 1, kappa 1, plus omega power of alpha tau, kappa tau. Okay, and just for reference as well, the alpha naught in the normal form of alpha is called the degree of alpha. So this is completely analogous to polynomials, for example. In a polynomial, the degree of a polynomial is that, let's say, the greatest power of x that appears in that polynomial. So it's a similar kind of idea. Alpha naught is the degree of alpha. So what we're interested in, we also looked at previously, is if alpha naught is equal to alpha, then the normal form of alpha will simply be omega to the power of alpha. So I quickly went through this earlier in the video. In this case, alpha is equal to its own degree. Alpha is equal to its own degree. And we know that by theorem F from section 18, that omega to the power of alpha is always greater than or equal to alpha. But a question that we've got to ask is, are there any such numbers such that omega to the power of alpha is equal to alpha? We've shown this inequality, but we've not actually exhibited any specific cases where equality holds. We can well believe that omega to the power of alpha ought to be greater than alpha, but can we actually exhibit a case where omega to the power of alpha is actually equal to alpha? So that's what we're going to be investigating in this section. And any such numbers, should they turn out to exist, are called epsilon numbers. So what we're interested in showing first of all is we're actually interested in showing the existence of epsilon numbers amongst the numbers of the second number class. So we're going to, theorem A concentrates on a way of showing that given any number from the second number class which is not an epsilon number, we can always generate an epsilon number from it. So in other words, the epsilon numbers are the solutions to the equation alpha equals omega to the power of alpha. So let's have a look at this theorem A from this section. I'm going to go through the proof also. So theorem A states that if gamma is any number of the first or second number class, which does not satisfy the equation omega to the power of psi equals psi. In other words, gamma is not a solution to this equation. It determines a fundamental series by means of the equations gamma 1 equals omega to the power of gamma, gamma 2 equals omega to the power of gamma 1, and in general, gamma to the power of gamma nu is equal to omega to the power of gamma sub nu minus 1. And the limit of this fundamental series, which we'll denote as E gamma, is always an epsilon number. Okay, so we know that gamma then is not an epsilon number. It does not satisfy this equation. So by theorem F of section 18, that must mean then that omega to the power of gamma must be greater than gamma. But omega to the power of gamma is equal to gamma 1. Here. So gamma 1, therefore, is greater than gamma. And by theorem B from section 18, theorem B, part B, if gamma 1, that should be there actually, gamma 1 is greater than gamma, then we've got omega gamma 1 is greater than omega gamma. But omega gamma is gamma 1. Omega to the power of gamma 1 is equal to gamma 2. So we've got gamma 2 is greater than gamma 1. And we can play the same game. So omega to the power of gamma 2 is greater than omega to the power of gamma 1. The result, gamma 3 is greater than gamma 2, sorry. In this way then we get a sequence. Gamma smaller than gamma 1, smaller than gamma 2, smaller than gamma 3, etc. So this is a fundamental series. If it's a fundamental series, it must have a limit. So the limit of gamma nu we will call E gamma. So also by theorem B from section 18, we know that omega to the power of, the limit of omega to the power of gamma nu is equal to omega to the power of E gamma. But omega to the power of gamma nu is simply equal to, if we think about our formula up here, it's going to be gamma sub nu plus 1. But the limit of gamma sub nu plus 1 is just equal to E gamma. In other words, E gamma is equal to omega to the power of E gamma. Well, that's exactly the definition of an epsilon number. So in other words, the limit of this fundamental series is an epsilon number. So in this way, given more or less any number, any random number from the first or second number class, we can always obtain from it, by this means, an epsilon number. So this is theorem B from section 20, which says that the number epsilon naught, which equals E1, which is defined to be the limit of omega sub nu, where the omega sub nu are defined in this way. So omega 1 is equal to omega 2 is equal to omega to the power of omega 1, omega 3 is equal to omega to the power of omega 2, and in general omega sub nu is equal to omega to the power of omega sub nu minus 1. It's the least of all the epsilon numbers. Okay, so let epsilon primed be an epsilon number, any epsilon number. Then what we've got is that epsilon primed must be greater than omega. And the reason for this is that omega is not an epsilon number. Omega is the smallest transfinite ordinal. epsilon primed must be a transfinite ordinal because there are no finite epsilon numbers. And since omega itself is not an epsilon number, and it's quite easy to see that it's not, then epsilon primed must be greater than omega. But remember also that omega is equal to omega 1. So what we're saying here is that epsilon primed is greater than omega 1. Using theorem B from section 18, we can say then that omega to the power of epsilon primed is greater than omega to the power of omega 1. But omega to the power of epsilon primed, because epsilon primed is an epsilon number, that's epsilon primed, that must be greater than omega to the power of omega 1 is omega 2. And we play the same game. Omega epsilon primed is greater than omega to the power of omega 2. This is again epsilon primed, that's greater than omega 3. So what we see in general is that epsilon primed is greater than omega nu for all nu, for all finite nu. So what we can deduce from this then is that the limit of the omega nu, because they are a fundamental series, the limit of the omega nu must be less than or equal to epsilon primed. But we've already said that the limit of omega nu is what we call epsilon naught. So in other words, epsilon naught is less than or equal to epsilon primed. We know by theorem A that this this limit here is then definitely an epsilon number, because this is a fundamental series, and omega is not an epsilon number. And epsilon primed was any epsilon number, any other epsilon number. Again, we don't necessarily know that such an epsilon primed does actually exist, but this is on the hypothesis that there is another epsilon number, then either it's going to be equal to epsilon naught, or if it is genuinely different to epsilon naught, then it must be greater than epsilon naught. So when you look at this here, what you can kind of see happening is that you're getting a sequence of something like omega to the power of omega, omega to the power of omega to the power of omega, and on and on and on. So omega to the power of omega to the power of omega to the power of omega. So this sequence, maybe it's not necessarily to be taken too literally, but it's almost like you this epsilon naught is going to be like an omega to the power of itself an infinite number of times. I mean, it's just a rough visualization, not necessarily to be taken too literally, but if you kind of visualize it like that, you can see why, in this particular case at least, you will get an epsilon number at the end. Because if you just stick if you've got omega to the power of itself an infinite number of times, and then you raise omega to that power, then you've still basically got the same kind of expression. But anyway, that's the proof of theorem B. Let's move on to theorem C. So let's have a look at theorem C then, which is if epsilon primed is any epsilon number, and epsilon primed is the next greater epsilon number, and gamma is any number in between epsilon primed and epsilon primed, strictly in between, then the epsilon number generated by gamma, in the sense of theorem A, must be equal to epsilon primed. So let's start with this inequality. Less than primed. And applying theorem B from section 18, we get that omega epsilon primed is less than omega to the power of gamma is less than omega to the power of epsilon primed. Because epsilon primed and epsilon primed are epsilon numbers, then that's equal to epsilon primed. This is equal to epsilon primed. Using the notation from theorem A, this is going to be gamma 1. Doing the same thing, we get that omega to the power of epsilon primed is less than omega to the power of gamma 1 is less than omega to the power of epsilon prime primed. Epsilon number, using the notation of theorem A, this is going to be gamma 2. So in general, what we see, continuing this process, we get that epsilon prime is less than gamma nu is less than epsilon prime primed, and this is for all nu, for all finite nu. So we know that the gammas, gamma 1, gamma 2, form a fundamental series, and their limit is this E gamma. So the limit E gamma, which is equal to the limit of gamma nu, must be less than or equal to epsilon prime primed. And because we know that this limit cannot be, it can't be equal to, it must be strictly greater than epsilon primed, because all of the terms of the fundamental series are greater than epsilon prime, so the limit itself must also be greater than epsilon prime. And we know that E gamma is an epsilon number, then it must be equal to epsilon prime primed. Okay? Because all of the terms of the fundamental series are strictly less than epsilon prime primed, the limit can't suddenly jump over epsilon prime primed. So what we can conclude then is that E gamma is equal to epsilon prime prime. And this is great for us because it means that we've got a way effectively of generating new epsilon numbers from old epsilon numbers. So we've already shown the existence of one epsilon number in theorem A, that we've already shown how to get the smallest epsilon number in theorem B. What this is saying is that all I've got to do to get another epsilon number is take a current epsilon number, current known epsilon number, add 1 to it, and then go through the procedure from theorem A, and that will generate another epsilon number. Not only another epsilon number, it will be the next epsilon number, the next greatest epsilon number in magnitude. So this gives me a way of generating ever more epsilon numbers. So what I've just said can really be summed up in this theorem, theorem D. If epsilon primed is any epsilon number, then the epsilon number generated from epsilon primed plus 1 is the next greater epsilon number. So this is the number generated in the sense of theorem A by epsilon primed plus 1, because epsilon primed plus 1 is not itself an epsilon number, not difficult to show that. So by theorem A, it will generate an epsilon number. And in this way we can generate from, let's say, epsilon naught, which was our smallest epsilon number, we can generate the next epsilon number, which is going to be epsilon 1 is equal to E of epsilon naught plus 1. And then we can get epsilon sub 2, which is just going to be E of epsilon 1 plus 1. And this is going to be the next epsilon number to epsilon 1, which in turn is the next epsilon number along from epsilon naught. So in this way we can get a sequence of epsilon numbers: epsilon naught, epsilon 1, epsilon 2, epsilon nu, etc. But this is not all of the epsilon numbers. This is not the only way that we can generate epsilon numbers, and that's where theorem E comes in. So if epsilon primed is any infinite series of epsilon numbers, one example of which would be this, with epsilon less than epsilon prime, etc., then the limit, so in other words, we've got a fundamental series, so we can speak about its limit, then the limit of this fundamental series, limit of epsilon nu, is an epsilon number, and in fact is the epsilon number which follows next in order of magnitude to all of the epsilon nu. So here in this particular example, we can go as long as we want, but we could never get to, for example, epsilon omega. We could never get there. Not just using this particular process. To get to epsilon omega, we would need to use theorem E. So let's have a look at... this is really just an application of theorems A, some combination of theorems A, B and C, theorems maybe A and C to prove D. E, let's have a look. Well, the limit, because this is a fundamental series, it has a limit, so the limit of epsilon nu is equal to the limit, because epsilon nu it is for each nu an epsilon number, that's going to be limit of omega epsilon nu. But by theorem B from section 18, the criteria D, this is going to be equal to omega to the power of effectively the limit of omega e nu. So it's getting kind of messy a little bit, but this is omega to the power of the limit that's written here. So in other words, because remember that epsilon nu is an epsilon number for each nu, then this is going to be omega to the limit of epsilon nu. So in other words, we've got that the limit of epsilon nu is equal to omega to the power of the limit of epsilon nu. In other words, this limit here is an epsilon number. It satisfies the criteria for an epsilon number. And the fact that it's the next epsilon number in order of magnitude to all of the epsilon nu follows from the fact that the limit of any fundamental series is the next in order of magnitude to all of the terms of the fundamental series itself. Okay, so let's have a look at theorem F, which is the final theorem that I'm going to go through in any detail in this video and indeed in this series of videos. So theorem F says the totality of epsilon numbers of the second number class forms, when arranged in order of magnitude, a well-ordered aggregate of type omega, which we use to represent the type of the second number class, and so has power Aleph1. So in a way this is a little bit surprising, a little bit counterintuitive, because what it means is that in the second number class, if we take all of the epsilon numbers in the second number class, there are as many epsilon numbers there as there are numbers in the second number class. So this is in many ways quite surprising, but it's completely analogous, at least from my perspective, to the kind of counterintuitive result that there are as many real numbers in the interval 0, 1 as there are on the whole real number line. So even though the whole real number line contains the interval 0, 1, there are as many numbers there in the open interval 0, 1, there are as many numbers there as there are on the whole real number line. It's a similar kind of result here, and it's really just, infinity just doesn't work in the way that we expect finite quantities to work. It behaves in a completely different way. So it is surprising, but it shouldn't be surprising in many ways. Okay, so let's have a look then. So let's arrange our epsilon numbers in order of magnitude. So starting with the smallest, we've got epsilon naught, then we've got epsilon 1, epsilon 2. Eventually we're going to get to epsilon omega, then epsilon omega plus 1. And in general we're going to have epsilon alpha. So alpha is just going to be a general number from the second number class. Okay, so because we've got each of these epsilon numbers are ordinal numbers, they're ordinal numbers themselves, and we've arranged them in order of magnitude, then by section 16 theorem C, the totality will form a well-ordered aggregate. So we've got the first bit sorted out that all of these are going to form a well-ordered aggregate. What we want to show now is that this alpha does genuinely range over the whole of the first, really the second number class, that there are no numbers missing from the subscripts. So notice that the subscripts here, they go in the usual order of ordinal numbers, 0, 1, 2, 3, 4, 5, up to omega, then omega plus 1, omega plus 2, omega plus 3, etc. And also notice that the subscript will determine effectively how that epsilon number is generated. So if the subscript is finite, or if it's a number from the second number class of the first kind, then that epsilon number can be generated through an application of theorem D, effectively. On the other hand, if we've got a subscript that is a number of the second kind from the second number class, such as the omega here, then that epsilon number will be obtained through an application of theorem E. So let's suppose, just for the moment, that there is a value, there is a number somewhere in the second number class that is not accounted for, that alpha doesn't get to. Let's say it's alpha primed. Okay? There must be a least value. Remember, any sub-collection or sub-aggregate of a well-ordered aggregate is itself well-ordered. So if there are any values that are not accounted for by this alpha, then these values, these exceptional values, will form an aggregate, a well-ordered aggregate, and therefore there must be a least one. So let's say that alpha primed is the least one that is not accounted for among the subscripts. So if alpha primed is of the first kind, then all I do is just take the previous epsilon number, or the epsilon, shall I say the epsilon number with subscript alpha primed minus 1, add 1 to this number, and apply theorem D to it. And this is going to give me the next epsilon number along in order of magnitude. Well, that would be, in that case, then epsilon sub alpha. So suppose then that alpha primed is actually of the second kind. So in this case, what I'm going to do is I'm going to take a fundamental series, beta nu, such that the limit is alpha primed, and then I can take the limit of the epsilon numbers with those betas as subscripts. Well, we know that this is going to be an epsilon number by theorem E. Not only that, it's going to be the next greatest epsilon number in order of magnitude. So what we're going to see then is that effectively we're going to get the epsilon alpha primed that we were after. So in other words, alpha must range over all of the numbers from the first number class and the second number class, whether it's a number of the first kind or a number of the second kind. Okay, so there's no gaps there. So let's think about the type of this aggregate that we've got here. Now, if you look, we've got all of the numbers, the subscripts range over all of the numbers from the first number class, omega, lowercase omega, and then the subscripts range over all of the numbers in order from the second number class, and that's capital omega. But that's not the type that we wanted to show that this had. We wanted to show that this aggregate has, its type is just capital omega. Okay, so we can do a little bit of fiddling about with the algebra here. So we can say this omega here by, I can't remember exactly which theorem, but we can write it as omega squared plus capital omega minus omega squared. So these are just arithmetical properties of ordinal numbers. but omega plus omega squared is just equal to omega squared, again using arithmetical properties here. So maybe I could be a bit more strict about this and say, right, we're substituting the omega here with this, and then I'm going to use the associativity to say that this is equal to omega plus omega squared plus omega minus omega squared. But omega plus omega squared is just equal to omega squared plus omega, capital Omega minus lowercase omega squared. But then omega squared plus capital Omega minus omega squared is just equal to omega. In other words, the type of this aggregate here is just capital Omega. And finally, we can just show that if, let's clear a little bit of space somewhere, maybe here. If omega, lowercase omega plus uppercase omega equals that, then the cardinal number of this is equal to the cardinal number of capital Omega, and the cardinal number of capital Omega is Aleph1, which is what we needed to show. So we've proved the theorem. So that brings us to the end pretty much of this video and this series of videos, in fact. There are a couple more theorems in section 20 that I've not covered, which are theorems G and H. The reason that I'm not going through them is because I think they're kind of, in a way, anticlimactic in comparison to the theorem that we've just proved. So I think this is a nice theorem to finish off on. Theorem G just considers some basic arithmetical properties of epsilon numbers, and theorem H is concerned with solutions to this equation, which is similar to the kind of equation that we've been looking at. We've been looking at so far the solutions to the equation omega to the power of psi equals psi. But now we've got a generalized version of this equation. We found that the solutions to this equation are the epsilon numbers, all of these epsilon numbers here. If we change the omega to a general alpha, alpha being a number from the second number class, then the solutions to this equation are all of the epsilon numbers greater than alpha. So they're still epsilon numbers, the solutions here to this equation, but they're just it's just a certain part of the epsilon numbers. There's some missing that would be solutions to this equation. So that's proved in theorem H, which I'm not going to go through in this particular video. And if you have made it to the end of these videos, then thank you very much for staying with me. There won't be another video in this series, but I will be making other videos on other historical works from mathematics, logic and philosophy. So if you are interested, then I strongly encourage you to watch some of those videos. But for now, thank you very much and goodbye.